So let's consider the sampling distributions of sample means. So what we're going to consider is a random variable x that is normally distributed in the population. And we're going to say that that population mean is 100 and it has a variance of 100 or 10 squared. So remember, in statistical notation, we would write x is described by the normal distribution on these two parameters, mu and sigma squared. And in our case, with this problem, we'll say that it's the normal distribution on a mean of 100 and a variance of 10 squared. So we can actually plot that distribution, and it's always good just to take pencil and paper and just draw this. So as per usual for this course, there is some code there, but please do not look at the code. You don't have to worry about the code. There's some pseudocode there. It's just reading what this code is supposed to do. So we're going to say plot the normal distribution given the parameters mu and sigma squared. And as I say, you can do this with pencil and paper. Have that idea in your head of this bell-shaped curve centered at 100 with a standard deviation of 10. So let's plot this just to see what it looks like. And there we go. As we expected, we see this normal distribution. It's centered around at 100, and we'll get about 68% of the values go from 90 to 110, and about 95% of the values are going to be between about 80 and 120. So there's our normal distribution. So what we want to do now is let's just simulate taking random values from this distribution. So we're going to assume we have random variables. And by that I mean we are going to draw from this distribution, and if I draw one value from this distribution at random, that's our random variable, is then realized. We have one observation, and I might do it again and again and again, and we're going to just think about taking 36. We're going to take 36 samples from this distribution. So 36 observations or 36 realizations of our random variable. And we're going to take those 36, and then we're going to calculate a mean. So we're going to have this x bar, the sample mean. And I'm then going to simulate doing this 1,000 times over. Now that's not a lot. And remember, this is not reality. There's no ways I can run a study and do that same study 1,000 times over. I'm just going to do that study once. But this is a computer, can easily do that. I'm going to simulate doing my study 1,000 times over. I'm going to take 36 values from this distribution. I'm going to calculate a mean. I'm doing this 1,000 times over so that in the end I have 1,000 sample means. Now don't do this on pen and paper. We can just use software and do all of this. So there's my pseudocode. I'm going to let x be described by the normal distribution on a mean of 100 and a standard deviation of 10 or variance of 10 squared, and I'm going to repeat the random selection of 36 subjects from this population 1,000 times and calculate the mean each time so that I have this 1,000 means, and then I'm going to create a histogram. So that's exactly what I do with the code here. We can ignore the code and look at that. By the Central Limit Theorem, we should see something that resembles a normal distribution. At least you can start to see that with this histogram. Although doing it 1,000 times is not nearly enough. Theoretically, we're thinking about doing this an infinite number of times. But we've done that 1,000 times. Now there's important things to remember. Now, we will always assume in a statistics course such as this that, unless we obviously state otherwise, is that our random variables are independent and identically distributed. By that we mean, independence we mean, let's take an extreme example. I might have homozygotic twins, and if they are both selected, then their values are not independent of each other. They're dependent on each other. So, that would be an extreme. So what we're just saying that these 36 values that we generate, they're all independent of each other. Or you can think about flipping a fair coin. No matter what the previous outcome was, heads or tails, that has no bearing on what the next outcome is going to be. These are independent. And we also want each random variable of those 36, we want them to be identically distributed. So they all come from the same distribution. So every time I select one of those 36, it comes from this very same normal distribution. So we're always going to assume that unless we state otherwise. So let's just assume that is so. Now, that means we can now consider questions such as the following. What is the probability that a sample mean in our example above is at most 98? Now, because we've simulated this 1000 means we can just look at how many of those 1000 were at most 98. So there were 98 and less. And that's what I do with the software here. I'm just going to calculate the number of these 1000 means that were at most 98. And if I run that code, I see it was 114. So what we see is that 114 of these 1000 means were at most 98. That's a proportion of 114 over 1000, or about 0.114, about 11.4%. So we can just probability and proportion, meaning the exact same thing. I'm saying the probability of finding a mean, if I do a study once, of at most 98 was only going to be 11.4%. Now, instead of simulating this probability from data, we can of course use the central limit theorem. The assumptions are met. We are told, remember there are two assumptions, we are told that this variable is normally distributed in the population and our sample size is 36, so that's at least 30. And so we've got both of those conditions met, and remember we do have those conditions met right up there. So we have these two conditions met, so we can make use of the central limit theorem. And that central limit theorem says that, well, these means, these sample means, should be normally distributed. And so what we can do, we are going to calculate a z-score, of course, because it's so much easier to work with a standard normal distribution. And there is our equation for transforming our mean into a z-score. And so we take a mean and we subtract from that mu. We divide by sigma divided by the square root of n. So when we're dealing with the mean, a sample mean, we do remember that we now have in the denominator a standard error. The standard error is the standard deviation of a distribution of sample means. So now we can state our problem in statistical notation, and we can demonstrate the probability in terms of a z-score, where remember z is described by the normal distribution on a mean of 0 and a variance or standard deviation of 1, so standard normal. And so there in line 1 here we have the statistical form of our problem. The question is, what's the probability that the mean, randomly selected mean, so in other words I go out, I select 36 random people, if that's the way that you want to see it as a good example, and I calculate a mean, what's the probability that that mean was going to be at most 98? So x bar less than or equal to 98. And I want to maintain that inequality, so what I do to the left hand side of the inequality I do to the right hand side. So on the left hand side I'm subtracting mu, on the right hand side I'm subtracting mu. Now remember we said the mu was, the population mean was 100. And then on the left hand side I'm going to divide by that standard error, that's sigma divided by the square root of n, and I do that on the right hand side as well. And that's always positive, so the sign's not going to flip. So 10 divided by the square root of 36, and if you use a calculator you should get negative 1.2. So the idea here is that this is exactly the same as this. The probability that z is less than or equal to negative 1.2. So the probability that a z value is less than 1.2 standard errors away from 0. Now always visualize this problem for me. Here's our pseudocode. I'm going to say visualize the PDF, the probability density function of the standard normal distribution, and the proportion of z-scores at most negative 1.2. So let's plot this. You do that in pencil and paper, and hopefully this is what you have. There's our standard normal distribution centered at 0, and this orange area here that goes from negative 1.2 towards the lower tail, it's this orange area. That's the proportion of the whole area under the curve, which remember, this is a probability density function. And so the area under the curve is 1. That's the probability of over all of the possible values of z. The proportion of that we're looking at is this orange section. So what proportion of 1 is that? Now that you cannot do with pencil and paper or algebraically. You have to use some software or calculator. So use your method of choice. I'm just going to use some software here, and I'm going to calculate that and look at that from a theoretical distribution In other words, using the central limit theorem, we're going to find a probability of z being less than negative 1.2 is 0.115. And look how close that was to our simulation. We just simulated this. We created 1,000 means, and we looked how many of those were actually 98 and less. It was very close to this. And so that's great. So we can conclude that the probability that the sample mean is at most 98 in this example problem is approximately 11.5%. Great stuff. Now I want to go to another example. I'm going to say the random variable x need not be normally distributed in the population. So now we're going to consider, if we consider an adequate sample size, we are just going to have this rule that we say we need at least study observations. Then we can invoke, or we can call upon, the central limit theorem. So in our next problem, we're going to consider a random variable x that is described by the continuous uniform distribution, and that is very far away from a normal distribution on the parameters a and b. So that's the continuous uniform distribution from a to b. So we can calculate a population mean, mu, and a population variance, sigma square, from the theoretical distribution. And so whenever you see mu and sigma, don't think that that's automatically attached to a normal distribution. You can have any set of numbers and you can calculate a mean and standard deviation from those numbers. That is not particular to a normal distribution. So for any bunch of numbers, you can always calculate the mean of those numbers, and you can always calculate a standard deviation or variance. But there's a way that we can do that. We call that the method of moments. So if your course does not include that, don't be concerned with this, the method of moments. So this is going to be the first moment. And again, I'm going to use some software here to calculate the first moment, or the expected value. And that's a mean. From this theoretical distribution, the uniform distribution with parameters a and b, and if I run that, that's very easy. It's a plus b divided by 2. And so that is very, very easy. You can also use this method of moments to calculate the variance. Now the variance is going to be what we call the second moment minus the square of the first moment. Again, don't worry about this. I've used some software here to calculate the theoretical variance of the continuous uniform distribution. And you see that that's a minus b squared. You could also say b minus a because you're just squaring that difference, divided by 12. That is the variance of this theoretical distribution. So let's put some numbers to this. So we're going to have this, we're going to consider a random variable x that is described by the continuous uniform distribution on the interval 10 to 20. So a is 10 and b is 20. And so we can calculate a population mean and a variance from this distribution. Now remember, 10 to 20, if I want to calculate the expected value, there it is, a plus b divided by 2. So it better be 10 plus 20 divided by 2. So that's 30 divided by 2, which is 15. And if I just use some software here, you're going to see, well, that's very easy. That's going to be 15. 30 divided by 2 is 15. So that works out. Here I'm going to calculate the variance. And again, it's just going to be 10 minus 20 or 20 minus 10, doesn't matter. That gives me 10 plus or minus 10, but that squared is 100 divided by 12. That's 8 1/3. So let's have a look at this. There you see 25 over 3. That's 8.333. Great. So that's from this example. Now we can plot this PDF. I just want to show you what it looks like. Please remember how, what the continuous uniform distribution looks like. There it is. There we can see it. That it is at a value of 0.1 when we are between 10 and 20 and 0 everywhere else. So if I look at this as probability density, 20 minus 10 is 10 times the height, which is 0.1. That still gives me this total area under the curve of 1.0. So this is a probability density function. So imagine that this is now our population. I went through all of this just to convince you of the fact. Don't worry about the mean and standard deviation and the method of moments here. Concentrate for me at the moment on this fact that this is not a normal distribution. So I'm going to now do the following. Again, a little thought experiment. So I'm going to take 49 observations and then I'm going to calculate a mean. So it's not from a normal distribution, definitely not, but I have at least 30. In fact, I've got 49 observations that I'm going to take every time. And then every time I select a random 49 values from this distribution, I'm going to calculate the mean, but I'm going to do this time I'm going to do it 10,000 times over. So I'm going to have 10,000 means. And that's what I simulate with the code here. I'm going to do that with code. And let's see. By the central limit theorem, what do you think the distribution of all these means are going to look like? There you go. It's nearly normally distributed. So this is not an infinite number. It's only 10,000. And it's very difficult to plot 10,000 values. So I'm actually behind the scenes. If you look at the code there, I'm selecting only 1,000 at random of those 10,000. Don't worry about that. We can all agree that there's a tendency for this to start looking like a normal distribution. And again, I can just look at something. So let's say I want to consider calculating the probability that a sample mean is at most 14.5. So in my simulation here, I can just say what proportion of these 10,000 means were at most 14.5. And I can use software here to do that. I just want to convince you of the fact, look at that. 1,086 of these 10,000 means were at most 14.5. And so that's 1,086 divided by 10,000. Again, that is about approximately 0.11. So about 11% of them. So instead of simulating the probability from data, we can call upon the central limit theorem. Our sample size was 49. That's more than 30 or more, I should say. So we're going to remind ourselves of this formula to transform our x bar value to z. And now we can state our problem in statistical notation. We are saying, under the conditions of this problem, what's the probability that a mean is at most 14.5? I do that thing of what I do to the left-hand side, I do to the right-hand side. So on both sides of the inequality, I'm going to subtract mu, which is 15. I'm going to divide by the standard error. Now, when we used that theoretical distribution and we had this from 10 to 20, it was 8 1/3. But remember, that was the variance. I used the method of moments there to calculate the variance. So remember, in a problem, I'll just tell you what mu in the usual exam situation, I'll tell you what mu and sigma is. You won't have to do this method of moments. I just wanted to go through that exercise so you can see where this comes from. And that was the variance though, so you do have to take the square root of that. So I'm saying 25 over 3, but I'm taking the square root of that because that has to be the standard deviation, not the variance. And then divided by the square root of the sample size, which is 49. And hopefully you get to z-score of at most negative 1.2. So immediately visualize this problem. Take pencil to paper, visualize the standard normal distribution, and I'm looking for this proportion of the area under the curve that is at most negative 1.2. So let's execute this code and have a look at it. There we go. There's our standard normal distribution. And we can see, oh, let's go. There we go, negative 1.2. So it's this proportion of the whole of all my values, my z values that are negative 1.2 and less. Again, you can use a calculator or software. If I use software, let's see what it is. It's 0.1126 or 0.113. And again, that is very close to our simulated values. So you can see that these things actually work. These theoretical distributions actually work for us. And the use of the central limit theorem really works for us. So I hope that these problems helped you to understand. And you can use this either to do your own lab problems or prepare for any kind of exam.